All right, welcome back for another episode of Con E 352. This is going to be the last section of testable material before exam 2. All right, let's get started and let's pick up with a discussion of energy, utility companies, energy charges, demand charges, and then we'll do a little example calculation where we compare two alternative HVAC systems and try to do a calculation that'll show you which one is the best one if we're defining best as the most cost effective. Cost effective, not necessarily the most efficient, but the most cost effective. Very frequently, those two terms, people mean the same things, but they are not always. And if we're going to talk about efficiency as the amount of energy a system uses versus the cooling or heating effect that it produces, that's fine, but efficiency is a little different than something that is cost effective. In other words, to get the same amount of heat, we want to pay the least amount of money. All right, so let's take a look. A couple things that you're going to need for this. The last few pages, I'm on page 71 of the section 2 packet. You want to grab that. And then I'm also going to have a PowerPoint on energy calculation. It'll say something like ground source heat pump versus furnace. And it'll be a PowerPoint presentation. But first, let's start with trying to explain what a demand charge is. Most residential energy rates are just that. They're just paying for the commodity. You pay for however many therms that you use for gas. You pay for how many kilowatt hours that you use for electricity. It's very, very straightforward. Sometimes on a residence, they'll have different energy rates for different times of the year. Sometimes, say electricity, if it's going to be different, it is usually cheaper in the winter and usually more expensive in the summer. Now, for commercial buildings, it gets a little more complicated. Yes, there's the commodity charge, but this is the demand on the grid. Think of this as like a citywide or maybe even statewide energy consumption. Think of the total amount of energy, and this is electricity, being used. If this represents how many kilowatts are being consumed in a one period of time, we'll have peaks. It'll be highest in the summer and usually lowest in the winter. All right. Now, there'll be some electric heat, which maybe this low point might occur in early fall, perhaps, and we'll have another low point in the spring. But by and large, the most demand that a grid is going to have, and like I said, whether we're talking about a city, a state, maybe an entire region of the country, the most consumption at any one period of time we're going to have is in the summer during the day. That is always the peak demand time. All right, and demand being how much power does a utility have to provide. Now, here's the thing, though. If you're a utility company, this is not how you would prefer people use power. The reason being is that there are limitations to how much electricity that you can generate, and, especially here in the United States, limitations for how much electricity we can distribute over the grid. In some parts of the United States, especially the Northeast and the Southwest along the California coast, our grid is about maxed out. Distribution systems are very difficult to build. The overhead power lines, obviously here in Iowa, we just experienced kind of a crisis of power distribution right after the hurricane. And they were able to get that back surprisingly fast. The power companies and the linesmen were able to get that put back together in surprisingly, shockingly short amount of time. But understand, the routes were already planned out. All the design work was already done. The right-of-ways, the easements, the the construction part of it, the planning was already done. We were just fixing what was already there. So that was pretty easy. Increasing the distribution capability of any grid is very, very time consuming and expensive and difficult, and most likely power companies would prefer not. They would prefer that this peak wasn't so high, and they'd prefer that this dip wasn't so low. And here's why. If you're a power company, you've got to put in all the infrastructure for this max, but maybe you're only providing that much electricity for a few hours a year. So you've got to have power plants, you've got to have wires and distribution and transmission lines for this maximum that you don't have to provide very often. So how do you get people to change their behavior? Well, no matter how many public service announcements you make about, turning down the electricity while you're not at home and using the minimum amount of electricity during peak usage times, that really doesn't work. What does work is when you hit people in their pocketbook, and I'm talking individuals, but also businesses. So this is the demand in kilowatt hours, but this is also represents the demand charge. Utility companies will charge individual customers based on their peak demand in kilowatts. And a lot of times they'll monitor the consumption by individual customers in 15-minute increments and try to find out, well, what was their peak demand for their whole month, and then hit them with a demand charge based on that peak. A demand charge is the price that a customer pays to have all this infrastructure in place to hit this maximum demand. So consumption is an important part of managing a customer's electric bills, but managing this demand is also a very important part. Now, we're not getting into this really deeply in this class, but if you're interested in this subject, I teach another class on it, Connie 354, on the energy code, which talks about the energy code and goes into electric bills a lot more in depth than we have time to do here. All right, but I just want you to understand that demand charges are based on the peak demand for an individual consumer within that 1 month. And they can be as great as the total consumption charge as well. And it's the price that you pay for the electricity company being able to have all this capacity and then have it sitting around part of the time. And that's where this demand charge becomes necessary. Because for a power company to have all this production capacity so that it's there on the worst few months of the year for a few hours during the middle of the day, that costs them, so they have to pass that cost on to their consumers. Now, most of the time, if we look at demand, and if this is electric demand, and here's that peak that I was talking about, the cheapest dollars per kilowatt hour of electricity production are always going to be coal-fired plants and nuclear energy. That has changed a little bit, all right? This used to be the case. That's always true. However, gas-fired engines, turbines, natural gas-fired turbines that produce electricity have gotten a lot cheaper. They used to be the expensive peak capacity generation. They used to be the more expensive one. However, that's not necessarily the true anymore. Natural gas has gotten so cheap that gas-fired turbines that produce electricity have gotten a lot more cost-effective on an hour-by-hour basis of operation. Couple that with the expense of coal in terms of not the coal itself. The coal itself is fairly cheap. The expense of maintenance on those facilities, but also cleaning that and removing the particulate. Coal is not used as much. It's almost impossible with regulations today to open a new coal-fired plant. So in the last 10 years, I'm going to say, and definitely within the last 5 years, most of the additional power generation capacity that power plants have brought online has probably been natural gas-fired turbines. That and something that isn't in this particular slide, but the wind energy, especially here in Iowa, has gotten to be a lot more prevalent. There's been a lot more wind turbines brought online, and the dollars per kilowatt hour is getting more competitive. It's not the cheapest alternative. Don't think that. Coal is way cheaper. Natural gas is cheaper. But for a power company, putting up wind energy plants is a lot easier regulation-wise. They don't get as much grief from the general public. The people that run around and, protest and tie themselves to bulldozers. Yes, that really happened. If we go back about 15 years, Mid-America Energy was going to build another coal plant by Marshalltown. They had the permits. They had the land all set aside. They were ready to build. It was going to be like $200 million worth of construction. And lawsuit after lawsuit after lawsuit was filed. Protesters were there, chaining themselves to bulldozers and creating a nuisance in general. After enough of that, Mid-America Energy just says, fine, we won't build the power plant. We'll put up wind turbines, because no one gets upset with us over the wind turbines. Now, the wind turbines have a pretty large tax incentive. And if they didn't, I don't think that they would be as cost competitive as the other alternatives like gas and coal. But currently, they do have a pretty big tax incentive for the turbines, or for the wind turbines. So people put them up. All right. So let's move on from this demand, the idea of demand charge, the cost that you pay to have that capacity ready. Just know that it's extensive, and it can change the way some people and some businesses operate their businesses, or operate their cooling and heating systems. All right. And electric rates. Sometimes during the low consumption times of the year, some power companies will offer cheaper rates in the winter to give people incentives to have electric heat, like ground source heat pumps. If we go back to this curve, what they're wanting to do is the power company would much rather people used a little less electricity in the summer and a little bit more in the winter. In other words, they've got to have a certain amount of generation capacity. Well, they've built it. In the winter, they realize a lot of consumers use natural gas to heat their buildings. They'll give incentives and cheaper rates in the winter for electric heat, like the geothermal heat pump systems. They'll give consumers incentives for those and cheaper rates in the winter, because they know if you're an owner building a building and you've got a choice between electricity and natural gas, a lot of them are going to pick natural gas, but the electric companies would rather sell some more energy in the winter, since they've got the capacity, for cheaper. And that's why these cheap rates in the winter exist. They want to give people incentive to maybe go with the heat pump. These incentives were a lot more prevalent, in the late 90s, early 2000s. Some of them have gone away, and we see fewer incentives like all electric winter heating rates. They do still exist, though, in some utilities, in some locations. All right. Let's see here. Oh, I have a few examples here of different prices. Electricity, a commercial consumer to this day, a lot of the commercial consumers in the Des Moines area, the big electric consumers, they're probably paying between 3 to 4 cents a kilowatt hour for the electricity. That does not include the demand charges. I just want you to know that. But this rate right here is why, if you look back in the 80s and the 90s, a lot of the high-rise buildings built in Des Moines had electric heat. it was even cheaper. In the 90s, the consumer or the large consumers in downtown Des Moines, they were paying like 1 penny a kilowatt hour, which is an amazingly cheap rate. So a lot of the downtown buildings had electric heat because it was cheap. It's cheap electricity. It's cheap first cost compared to natural gas-fired boilers back in the day. So a lot of them had electric heat. And if you go into remodel one of the buildings in downtown Des Moines, you may very well see that. It's not as cheap anymore, but it's still fairly cost-effective. If you look at, there's just a couple of comparisons here, like Ames, a residential consumer, might be at 8 cents a kilowatt hour. If you're in a rural co-op, like you're outside of a town, 13 cents and up a kilowatt hour, maybe 15 cents might be a better number to use right now. So anywhere here in Iowa from 3 cents to 13 cents, and that, remember, that doesn't include demand charges. As a comparison, if you look at the electric rates in Southern California, even our rural co-op is a deal compared to the electricity rates in California. Electric rates in California are anywhere from 25 cents to, in some areas, 40 cents, plus demand charges. Electricity in California is incredibly expensive. And there's areas around the world that are far worse than that even. So we pay some of the cheapest electricity here in Iowa that's available in the world. Important thing to note. Because of that, because of the varying electric rates from city to city to state to country to country, the best system for one location could be very different from the best system in another part of the world. And knowing the electric rates is everything towards choosing a heating and cooling system. All right. Now, I'm going to give you an example here. Yeah, let's switch over to the PowerPoint slides. All right. So go to this handout. There it is. All right. We're going to compare a ground source heat pump versus a furnace, and we're going to do an energy calculation. And I'm only going to do the heating because that's just the easiest, and it's a good comparison to take a look at. So we're going to compare natural gas versus electricity in a heat pump system. And I went through this particular example actually comes from a conversation that I had years ago with one of our alumni, one of my former students. He and his wife moved to the rural Madrid area. They're on an electric co-op. They bought this house. It was an older house. And he calls me up. He says, Mr. Perkins, what do you think? Should we put in a ground source heat pump in our house? It has a furnace now, but I'm thinking of putting in a ground source heat pump. And we went through this discussion and kind of weighed the economic advantages and disadvantages of the two options. And so I thought, this is a really good exercise. I'm going to incorporate it into my class. So let's just take a look. So student calls, former student, alumni calls, says, hey, we've got an LP furnace. I'm just kind of wondering, should I rip it out and replace it? I'm like, okay, let's analyze this. So, and the reason he was asking is he had heard that heat pumps were efficient. He says, I've heard they're really efficient. Would this make sense for us to replace our existing furnace with a heat pump? I'm like, okay, well, let's just take a look. I asked him, I go, how efficient is your furnace that you have right now? And he's like, well, I don't know. How would I know that? And I said, well, we could, the odds of him having a manual on it are slim. Maybe there should be a stamp on it somewhere on the outside of the furnace. But I just asked him a simple question. I said, hey, on the vent for your furnace, is it PVC or is it steel? And does it come through through the foundation wall of your basement somewhere? Maybe between the couple feet right above grade there. Does it stick out through the side of your house? Can you see it? And he's like, yeah. He goes, it's just a PVC pipe sticking out through the side. And this tells me something, and it should hopefully tell all of you something about the efficiency of that particular furnace. Because they're venting it through the sidewall with PVC, that means that the temperature of that exhaust is very, very low. That tells me that this is a high efficiency furnace, high enough that it is condensing. Because it is a condensing furnace, that tells me it's greater than 88% efficient. And for the purpose of this calculation, I just assumed it was 90% efficient. Could be higher. They make furnaces a little bit higher, 94, maybe even 95 or 96% efficient, but I just assumed 90% for the purpose of this calculation. All right, so then I asked him, how much LP did you buy last year? And he said, well, I think we spent about $1,000 in LP for the year. And then I asked him, what were you paying? And it was just under $1 a therm. And I put it here as 95 cents a therm. All right, so we got some, from that, we can calculate how much heat did he need to buy for the winter last year. All right, and then we're going to compare that. We're going to figure out how much heat he needed to have in the house in just a second. But then, and then after that, we're going to compare that to a ground source heat pump. And I just assumed that the efficiency of the ground source heat pump would average about a COP of about 3 in winter. And we'll come back to this in a second. But first, let's go to the next slide and let's take a look at this gas consumption part. Said, all right, if you purchased $1,000 worth of LP and the price per therm was 95 cents, that tells us something important. In other words, to get through the year, his furnace consumed 1,053 therms of propane over the course of that winter. Now, remember though, if we convert that, and that's what this next is, converting the therms to BTUs of potential energy, all right, I've got to multiply that by the efficiency of the furnace right here to get how many BTUs of energy actually went into the house. He purchased over 1,000 therms, but because of the inefficiency of the furnace, not all of that energy went into the house. So that's why it's important to know the efficiency of the furnace. So converting that, 94.77 million BTUs went into the house. In other words, that was my net effect. So now what we have to do a true comparison between different energy sources, natural gas burning furnace versus a heat pump using electricity, we've got to figure out, all right, it cost this homeowner $1,000 to get this much heat into the house. What would it have cost to get an equivalent amount of heat and electricity? Then a quick review here. If you look at the far right, warm house, cold environment, the picture on the far right where we were trying to heat a house using a heat pump. And that cold environment is the ground. We're trying to pull energy out of the ground and use that in a heat pump. I just want to quickly review this right here. The coefficient of performance for a heat pump is the ratio of the desired output over the required input. And here, the heating effect over work input, we can measure both of those in kilowatt hours. Understand though, work input is in kilowatt hours of electricity. Heating effect is in kilowatt hours of heat. Understand the difference. These terms are used for energy, but in one case that's energy in the electricity form, and the other case that's energy in a heat form. So for our heat pump, the coefficient of performance is greater than 1. In other words, if we go over to that picture, that heat pump transfers more energy into the house than it consumes in electricity. All right. So with that in mind, let's turn to let's try to answer the question, what would this same amount of heat cost us? Well, to get 94.77 million BTUs, first I have to convert this type of energy in British thermal units into kilowatts. Kilowatt hours. All right, so going from 27,000 kilowatt hours, right, and this conversion, that should be 1 kilowatt hour to BTUs. All right, not kilowatts per hour. It gets a little confusing here, I realize, because in English units, an energy rate is BTU per hour, and an energy rate in metric is kilowatt. A kilowatt is a rate. A kilowatt hour, 1 kilowatt for 1 hour, is energy, which is BTUs. The hour part totally messes people up. If you don't understand that part, pause. You may have to, Google the conversion until you're comfortable with that conversion. If my explanation isn't enough, I want you to pause right now and find it until you're satisfied that you understand it. Okay? So back here. So doing this conversion, we got 27,775 kilowatt hours of heat in the house. That's the same quantity as this in million BTU. Now, knowing that efficient has that the efficiency of the heat pump would have a coefficient of performance of 3. That means if I wanted that 27,000 kilowatt hours of heat in the house, I'd have to consume a third of that in kilowatt hours of electricity. So to get this much heat in the house, I had to consume 9,258 kilowatt hours of electricity. Next step is, well, what would that 9,258 kilowatt hours cost us? And I just used 13 cents a kilowatt hour for a rural co-op as an example. So we did this analysis, and my student said, wait a minute, it would cost me more. It cost $1,200 to run the heat pump, but it only cost me $1,000 in natural gas or LP gas last year. It's like, I'm confused. I thought heat pumps were efficient. I said, they are efficient. They just might not be the most cost effective where you're at your rate. Look what it would be, say, in Ames or maybe even Des Moines. You could get the same amount of heat at 8 cents a kilowatt hour for $741. And at 5 cents a kilowatt hour, you can get the same amount of heat for $463. That's a huge difference. So I said to him, hey, which co-op are you on? And he said, I want to say he was on Midland Power. I said, Midland Power has a special winter rate for heat pumps at 5 cents a kilowatt hour. He says, oh, okay, well, that changes the economics now, doesn't it? But here's the thing, is that it's not enough. He's like, okay, so maybe he could save $500 a month in heating costs, but is that really enough to justify the first cost of that furnace? Or I'm sorry, the first cost of the heat pump instead of another furnace. So to analyze this, what we've really got to do is, all right, so before I replace anything, what would the two options cost me? If he could replace his existing unit for $8,000, and that's a pretty good number. Just last year, we had to replace a furnace in our house. So think of that as like the cost to pull an old one out and put a new furnace and air conditioning unit in, $8,000. then the cost to pull the old furnace out and replace it with a heat pump that used the same ductwork and everything, notice the cost here, about $5,000 for a 5-ton heat pump. But the super expensive part is this. If you had to drill 5 wells or put in 5 bores in a bore field at $3,000 each, your total incremental cost is now $20,000 versus $8,000. And the question is, do you spend an extra $12,000 today to save yourself just over $500 a year? Well, there's the question. Do you pull that system out and replace it with something more expensive if all I'm going to be doing? I mean, would you spend $12,000 today to save $500 a year in heating bills? Now, this analysis ignores any savings that might happen during cooling. All right, so they're probably going to save more than $500 a year, but still, $12,000 is a pretty steep first cost. Even if you were able to save just as much in summer as you would in winter, which is probably not the case, but you know, for a residence, it's probably not the case. In a commercial building, it could be. But even if you could save $1,000 a year in your energy bills, would you really spend an extra $12,000 up front? And the answer to this question is this. And my question usually is, this is the point that I ask our students in class. It's like, hey, who remembers this cash flow diagram and the time value of money? And that's when people usually moan and groan and curse at IE 305. However, I would submit to you that this equation is far more important than anything you've learned in calculus. This is the same type of analysis that every construction project goes through. If I spend some more money on something and I'm hoping to get some payback for that, whether you say to yourself, I'm going to buy a new crane thinking I can save or rather bill out that year after year after year and ultimately make money off of it. Do I buy new equipment? Same analysis. Does an owner buy higher efficiency windows? Do they get the heat pump versus the furnace? They are all the same analysis. And I'm telling you that this is the most important math exercise that you're going to learn in your career here. So I hope you studied well. But back to this analysis, it's like, wait a minute. If this was 12,000 and this was 1,000 every year, do I take a risk that that's going to pay for itself? Well, what would we really have to know about this, about our equipment, to really know if this is a good investment? Some things you need to know. How long is the furnace and how long is the heat pump expected to last? I would hope that you'd get at least 15 years out of that heat pump and at least that out of the furnace, maybe hopefully longer out of the furnace. Heat pump, I would hope 15 years. Our heat pump in our house, and we have a water to air geothermal heat pump in our house. We installed that right about 16 years ago. Just a little bit longer. It might be 17 years and it's still running. So it's possible for it to last longer. So if your payback was 12 years, sure, right? But what else could go wrong with this analysis that would change the economics? Well, one is the expectancy of the equipment. Let's assume it lasts for the life of our analysis here. But really, what could change that equation? A couple of them is there anything that could lower the first cost of that ground source heat pump? If we go back to this number, is how could I make this $20,000 cheaper? Well, there's a couple of important ways. One, high efficiency equipment like heat pumps usually have energy rebates in the form of either rebates from the power companies or rebates from tax incentives. So a rebate up front could lower this significantly. Could be a couple $1,000. Also, take a look at the cost of this, the 5 bores at $3,000. What I asked him is, hey, at your house, do you have any land? He's like, yeah, we own a few acres of land. All right. Aha. I said, well, what you could do is do like I did on our system. And instead of hiring a well drilling company to put 5 wells in the ground, you could rent some equipment like a Ditch Witch. And if you have land, you could put in lateral lines that are, say, 5-6 feet down. And yes, you'd have to put in a few more feet of pipe, but the overall cost, instead of $15,000, I want to say we rented a Ditch Witch and I did my own. We did that for less than $5,000. Now, notice that. If instead of $15,000 worth of wells you drill, that you only put in $5,000 worth of lateral piping, that makes this a whole lot more attractive. So if the first cost was $10,000 versus $8,000 for the furnace, but you could save yourself between $500 and $1,000 a year in energy bills, that starts to make a lot more sense. Now, let's take a look at this. A couple of other unknowns in here. Gas price changes and electricity price changes. All right. Electricity rates change. And about the only direction electricity rates are changing is they're going up. I would not think that electricity rates are going down. Of course, 20 years ago, go back to this equation. 20 years ago, we were buying natural gas for $1.50 a therm too. So it's really hard to know where these energy prices are going. They're commodities. Electricity is going to change less in aggregate, or I should say, electricity is going to be less volatile. It will not go up and it will not go down as drastically as what we've seen with natural gas. However, natural gas is cheap. To be perfectly honest, at the current rate structures, with natural gas being less than $1 and electricity going up, I would have a hard time justifying that first cost, right? I'd have a hard time justifying a first cost of like $12,000. An incremental first cost of $12,000. That'd be hard to justify on a system like this that's this size. Maybe you could do it if you could get this a whole lot cheaper, perhaps, but it's still kind of risky. But here, this is the type of analysis that you have to do every time when an owner is saying, hey, I want the best system, the most cost-effective one, the most efficient, which is what they really mean is cost-effective. If we're making this type of analysis, you've got to do this. All right. Okay, so if you have questions on that subject, please let me know. And just as a reminder, this is the last subject material, last testable subject material on exam 2. Also, check the announcements. I'm going to have an announcement here shortly with regards to exam 2, but I'll cover it in the written announcements. All right. So good luck on the exam, and I will have an exam review session here before the exam. So stand by for that.